So are there any questions in the last lecture? Any doubts? Okay, so let's quickly review what we were doing. So in the last class, we saw the Gauss elimination method to solve a linear systems, right? So in particular, if I take the 3 by 3 system, which is A11 x1, so first equation is this. And the second equation is A21 x1 plus A22 x2 plus A23 x3. This is equal to B2. And the third equation is with the coefficient A31, A32, and the coefficient of x3 is A33. This equals B3. So we saw that how do we solve this this system, 3 by 3 system. In particular, we have seen it for n by n system using the Gauss elimination method, right? So what is the idea of the Gauss elimination method? That assuming that this coefficient here is non-zero, we eliminate x1 from the second equation and the third equation, right? And in the reduced system, which means that the new system which we get, we will not be having the x1 in the second and third equation. Then in that reduced system, we eliminate the coefficient of the x2 from the last equation. And finally, we get a system which will have the coefficient matrix as an upper triangular matrix, right? And then we solve by the back substitution. So this was the Gauss elimination method. So if you recall, we were keeping these assumptions that we started with A11 is not equal to 0, right? Or in general step, we were having that k, this is not equal to 0, right? So we'll try to see that how can we modify the Gauss elimination method so that we don't have to keep these additional assumptions. So this is a modified Gaussian elimination method, and the modification will be done by the partial pivoting. So I'm going to explain it for this 3 by 3 system again, and the same idea can be extended to any general n by n system. So let's call them, so this is a system 1, and I'm going to call this as E1, this is E2, and the third equation as E3. Okay, so note that what do we want? So if we want to apply the Gauss elimination, we will be dividing by this coefficient A11, right? So that's why we don't want to keep it, we want to avoid that this has to be 0, right? Likewise, after the first step, in the step 2, you will be having some different coefficient of the x2, and you will be dividing by this coefficient. So you don't want to have that to be 0. So that's why we are keeping these assumptions that these coefficients are non-zero, right? But how can we avoid this? So imagine that if we take, so you have the coefficients of x1 sitting in all the 3 equations, right? So if we take a maximum of all these 3 coefficients, suppose this maximum is occurring at A31. That is among A1, if we see in the magnitude, A31 is larger than A21 and A11, right? So what I will do, I'll exchange third row and the first row, right? Whether you solve these 3 equations in this order or you keep the third equation first and the first equation last, it does not make a difference, right? The solution is not going to change. So what I'm going to do, I'll exchange the third row with the first row, And then I will apply the Gaussian elimination, right? That I will eliminate the x1 from the next two rows using the coefficient which I will be having here, which I know is going to be non-zero because I'm taking the maximum of all, right? So this is the modification. This is how we are going to remove this assumption of the coefficients to be non-zero, right? So let's write it down. So the step one is going to be that I'm going to take the maximum of A11, A21, absolute value of the coefficients of x1. Okay, and let's call this maximum to be S1. Okay, so let's define S1 by this. Okay, so now what can you observe for this S1? That this is going to be non-zero. So do you agree with me on this, that this S1 will be non-zero? Because you're taking the maximum of all these coefficients. If this is zero, this means that the only possibility you can have that each one of them is zero. But if you have one row zero in the matrix, you will not have matrix to be invertible, right? So S1 has to be non-zero. Now, it might happen that, see, suppose you have whatever is the value of the S1 you are getting, suppose at the A21 and A31 you have the same value, right? Now, which one you will choose, whether you will exchange first row with the second row or first row with the third row, right? So this problem might occur. So for that, what we will choose, we'll choose the least integer, least number. So let's call it K. Let K be the least number such that S1 is occurring at the row AK1. Okay, so which means that if you have the same value, which is same magnitude, which is at the place A21 and A31, I will be choosing A21. Okay, because 2 is smaller than 3. Now, what is the step we are going to perform? We are going to exchange the kth row to the first row. So we interchange the first equation and kth equation. Right? So if we perform this interchange, what is going to be the reduced system? The modified system will be say we get it as A111 x1 plus A121 x2 plus A131 x3. This equals B11. So I'm using in the first equation, I'm using 1 in the superscript. So this I will do for all the equations. So the second equation is going to be A21 x1 plus A22 x2 plus A23 x3. This equals B2 1. And then likewise I will have the third equation. So this is going to be A31 x1 plus A32 x2 plus A33 x3 with the superscript 1. Now, how does these coefficients, these new coefficients relate to the previous coefficients? So note that what I have done, I've just exchanged the kth equation and the first equation, right? So only the coefficient of the kth equation will change and the coefficient of the first equation will change. Rest all the coefficients will remain as it is. So basically here A11 is, this new coefficient A11 is going to be AK1 because I'm exchanging the kth row and the first row, A12, this is going to be AK2, A131, this is going to be AK3. Now the new coefficients of the kth row, which are going to be AK11, AK21, and AK31. These will be the coefficients of the first row. So these are A11, A12, and A13. And we will have B1 as BK and BK as BK1 as B1. Okay, so this is the first step. So let's call it 2. And this again, I'm going to refer it as E1, E2, and E3. And let's call it as 3. So in this new system, you can observe that this coefficient is going to be non-zero. So I can apply the elimination step. That is, I'm going to eliminate x1 from E2 and E3. Okay, so this is the next step. And note that here, when we have done this exchange, this interchange of the equation, rest all the coefficients will remain as it is, except the one which I've mentioned here. Okay, so let me write this as well. So, and rest of the coefficients Aij1 are same as Aij as all equations other than the first and the kth equation. They remain unchanged. By the interchange of first and kth equation. Okay. So in this new system, I'm going to now eliminate x1. So this step is the same as the Gauss elimination, what we have done before. So we're going to eliminate x1 variable from E2 and E3 of system, which is 2. And for that, I'm going to define the multipliers. So we define the multipliers as, so M21 is going to be the ratio of A211 divided by the, so ratio of A211 and A11. So this is going to be A211 and divided by this coefficient. And M31 is going to be A311 divided by A11. Okay. So now what is the elimination step? So I have to perform. So basically I have to replace E2 by E2 minus. So I'm going to multiply the equation 1 by M21 and subtract from E2. Okay. And then for the third equation, I'm going to multiply M31 to the first equation, and that I am going to subtract from the third equation. So what is the new system after performing this step? So I'll be basically in the second and third row, I will not be having x1 there, and the rest of the coefficients will change accordingly. So the first equation will remain as it is. So this is as it is. Now for the second equation, let's call the new coefficients to be A22 x2 plus A323 2x3. This equals B2 2, and the last equation is going to be A322 x2 plus A33 2x3. This equals B3. So this is going to be 4. So let's number them as well. So this is 3, this is 4, and this is 5. So again, let me refer these equations as E1, E2, E3. So now what are these new coefficients here? So where these Aij's, they are going to be Aij 1 minus, so multiplying the multipliers. So this is going to be Mi1 times A1J 1. So this is for I and j equals 2 and 3. Okay, and the coefficients Bi 2, these are going to be the difference of Vi1 and multiplier Mi1 multiplied by B1. Okay, so note that here, if you see, everything is the same except that I have exchanged here the two suitable rows, so that I could remove this assumption that the A11 which I was assuming non-zero before, right? I did not require this same assumption now. So in the Gauss elimination, now if you want to remove x2, so we were keeping that this coefficient is non-zero, right? So that assumption as well I want to remove. So I'll perform the same idea. I'll use the same idea. I'll take the maximum of these two coefficients, right? So here I'm explaining it for the 3 by 3 system, but you can imagine what will happen when you will have an n by n equation. So you will take the maximum of all the coefficients, which coefficients of the x2 here, right? And then wherever the maximum occurs, right, you choose the least number and exchange it with the second row. Okay, so that we don't have to keep the assumption that A222 is non-zero. So let's perform that step. So this is step 2. I'll just repeat the same idea. So I'll take the maximum of A222 and A322, and let's call it as S2. Okay, so we can observe that this S2 will be non-zero, and let's take the least integer least number where this S2 occurs is L. So let L be the least number such that S2 is attained at AL2 2. Okay, so then I will interchange the Lth row to the second row. Or rather, let me write equation. To obtain this new system. So the first row will remain as it is. So for the second row, what we have, we are basically changing the second row with the lth row, right? So we'll get some new coefficients here. So let's call them A223, x2, and this next coefficient is going to change to A233, x3. This equals B23, and this coefficient will change to A32 and A333, right? Where A22 is going to be, A223 is going to be AL2, 2, A233 is going to be AL2, AL32, and B23 is going to be BL2. Okay, and I'm exchanging the second row with the lth row. So the lth row coefficient will be the new coefficients AL23. This is A222, and AL33. This is going to be A232, and BL3 is going to be B22. Okay, so for example, if L is equal to 2 itself, that is, if you take the maximum of A22 and A222 and A322 here, and if it occurs at the second, if A22 is in magnitude it is bigger than the A32, then basically there's no change happening in the system. Okay, you can directly apply the elimination step for the X2. Okay, so after this step, let's number this equations again. So this is 6, and I'm naming the equation as E1, E2, E3 again. So what I'll do now, perform the elimination step. That is, I will eliminate X2 from the third equation. So now we are going to eliminate X2 from E3 in system 6. So for that, we introduce this multipliers M32. This is going to be the ratio of A323 divided by A223. Okay, and note that now this coefficient is going to be non-zero. I'm not keeping this assumption. It is automatically non-zero because I'm taking it the maximum of the coefficient in that column. Okay, so now we use this multiplier to perform the elimination step. So I'm going to replace E3 by E3 minus M32 times E2. That is, I'm going to multiply the second equation by M32, and then I'm going to subtract it from the third equation. And the new system which we are going to get, you can observe that we will not be having X2 variable in the third equation. So the first and second equation will remain as it is. So we will have A111 X1 plus A121 X2 plus A131 X3. This is equal to B11 and then 8223 x2 plus 8233 x3. This equals b23. Now only the coefficient of the last equation will change. So this is going to be 8334 x3. This equals b3. So where this coefficient 834 is 833 minus M32 multiplied by so this will be 233. 8233 and B34 is going to be B33 minus M32 times B22. Okay, and you can observe that this final system which we have obtained, which is 8, the coefficient matrix here is an upper triangular matrix, so we can use the system by back substitution. Okay, so finally we solve the system 8 by back substitution. Back substitution meaning that you will first solve for the last equation for the x3, and then you use the second last equation to solve for x2, and then the first equation to solve for x1. So we use the back substitution to obtain x3, x2, and x1 successively. Okay, so this is the Gauss elimination with partial pivoting. Okay, so here you can see that if you just try to compare it as the Gauss elimination which we discussed in the last class, only thing I'm doing here is that I'm just performing that an interchanging of certain rows so that I have the largest coefficient as the pivot element. Okay. So let's take one example just to apply this partial pivoting. Suppose we have to solve the system, which is, so this is a 3x3 system I'm considering, 0.81 x2 plus 0.9 x3. This equals 0.6867 x1 plus x2 plus x3. This equals 0.8338. This is the second equation. And third equation is 1.1331 x1 plus 1.21 x2 plus 1.1 x3. This equals 1.00. So 00. Let me take yeah. So this is 1.001. Let me take 1 itself. So in this case, of course, you don't. You can directly apply the Gauss elimination and solve the system, but I just want to explain it using the partial pivoting. That how does this algorithm works? So the first step is going to be that I'm going to find the maximum of 0.729, 1, and 1.1331, which is nothing but 1.331, which is the same as the magnitude of the 831, right? So this is our S1. And just for the notational purpose, I'll use, say, I want to change the ith equation with the jth equation. So I'll use this sign. Okay, so this is for the interchange of row I and j. Okay, so this is just a notation I'll be using. So we can see that the maximum is occurring here at the third equation. So I'll be exchanging the first equation with the third equation, right? So I'm going to work with the augmented matrix instead, because in the final matrix, whatever we'll get the final matrix, we can write down in terms of the equations, right? Because you see that the position of the x1, x2, x3 is not changing, because I'm just applying I'm not working on the columns, I'm rather applying the operations on the rows, right? So it's not going to change the position of the variables. So I'm rather working on the augmented matrix. So let's take the augmented matrix. So this is going to be the coefficient matrix, which is 0.729, 0.81, 0.9, 1, 1, 1, 1.1331, 1.21, 1.1, and the right hand side vector is 0.6867, 0.8338, and 1. Okay. So the first operation which I'm going to apply here is the exchange of the row R1 and R3. So here when I write R1, this means I meant the first row, and R3 is the third row. So I'm going to exchange them. So the new system which I will get, this is going to be 1.1331, 1.21, 1.1, 1, and the first row will become third row, and second row will remain as it is. Okay, so now what I will do, I want to eliminate the coefficient of x1 from the second and third equation, right? So I'll make zeros here by using the multipliers, which are M21 and M31. So M21 is what? M21 is the ratio of 1 divided by this coefficient. So we can simplify it. I'm directly going to write it. This is 0.7513, and M31 is the ratio of 0.729 and 1.1331. So this is going to be 0.5477. You can use the calculator to perform these computations. Okay, so once we have these coefficients, I can use them to eliminate these coefficients here. So the reduced system is going to be, so basically I'm performing R2 is going to be R2 minus M21 times R1. And for R3, I'm performing R3 minus M31 times R1. So first equation will remain as it is. In the second equation, this entry will be 0. And I'm going to write down all the other entries after simplification. So we'll get them as 0.0909, 0.1736, and 0.0825. And in the last equation as well, we will have this entry to be 0. And the other entries, I'm writing it here, 2975, and this is 0.1390. Okay, so now what we'll do, so this is my new coefficient A22, and this is a new coefficient A32. So I'm going to take the maximum of both, and wherever the maximum occurs, I'm going to exchange that row with the second row, right? So I'm going to take the maximum of, so both are positive, so I don't have to write the absolute value here. So which is at 0.1473. So this is going to be S2. So which means that I have to exchange the second and third row. So I'm going to perform R2 exchange with R3. So this will give me this new system. So first row is as it is. Now second row will become 0.1473, 0.2975, and 0.1390. And the second row will become the third row. Okay, so now I'm going to eliminate x2 from the third equation. So which means that I'm going to compute the M32. This is going to be the ratio of this coefficient divided by this coefficient. So upon simplification, we'll get this as 0.6171. So I'm going to perform that R3 will be replaced with R3 minus M32 times R2. So the new system which we are going to get is this. So first row is as it is. Second row will remain as it is. And in the third row, this will be 0. And here I will get 0.010. And this entry here is going to be minus 0.00328. Okay, so this is the reduced system which we get. And let's call this coefficient matrix as U and the right hand side vector as G. So we can solve Ux is equal to G by back substitution. And you can verify, you will get the solution as x3 equals 0.3280, x2 as 0.2812, and x1 as 0.2246. Okay. So this is how the this method of partial pivoting works. All right, and you can like in the Gauss elimination and also today as well in the Gauss elimination with partial pivoting, we have seen that the final matrix which we get it as a upper triangular matrix. And these upper triangular matrices, when you have the coefficient matrix as the upper triangular matrix, you can easily solve them by the back substitution, right? So now we can ask a question that, okay, like we know that if we want to solve Ax is equal to B, we are assuming that A is invertible, right? But in the invertible matrices as well, can we have the classes of the matrices for which we can easily solve this matrix equation, Ax is equal to B, right? As we have already seen that once we have the upper triangular matrix, we can easily solve the system Ux is equal to G, right? So what are the other matrices we can have? So one can, the simplest one which we can have is the diagonal matrices. So let's see some classes of the matrices for which we can easily solve the system. So the following matrices whose structure is simple which makes the linear systems solvable readily. So the first example is the diagonal matrix, right? So we have the invertible diagonal matrices. That is, if you have the coefficient matrix as a diagonal matrix, which means that other than the diagonal, rest all the entries are 0. And let's take the diagonal entries to be d1, d2, dn's, right? And rest all the entries are 0. So this is how the diagonal matrix looks like. And I'm going to, since I'm having that this is invertible, I'm going to assume that di's is not equal to 0, right? So since it is invertible, we have that di is not equal to 0 for all I. And if you have this as a coefficient matrix, and if you want to solve Ax is equal to B, the solution is very easy, right? The xi's are going to be nothing but Bi divided by Di. So in this case, the solution vector X so we will have xi as Bi divided by Di for all I. Right? So this is the simplest case. If you have A as a diagonal matrix, you can easily solve it. Now, if we have A as a, say, lower triangular matrix, so we have invertible lower triangular matrix. So that is, these matrices basically have this form. So I'm going to have the entries above the diagonal, main diagonal, those are going to be 0. And let's call the diagonal entries to be Li I. So and again, since I'm having the invertibility of this matrix, so I have to assume that Li they are not equal to 0. Okay. And in this case, if you have to solve the system Ax is equal to B, which is going to be that we have this as a coefficient matrix L11, L21, L22, L2, Ln1, Ln2, Lnn, and we have the vector x1, x2 up to xn. This equals b1, b2 up to bn. So you can see that you can easily solve it. Like we can do it in case of the upper triangular matrix. So you start solving from the first equation. So we solve for x1 using the first equation. Then we use that x1 to solve for x2 from the second equation. And we continue this process up to we solve for the xn, right? So from first equation, we solve for x1. So x1 will be b1 divided by L1. Now we substitute this value of the x1 in the second equation and solve for x2. So upon solving, we are going to get x2 as b2 minus L21 times x1. x1 is b1 divided by L11, and this completes divided by L22. Right? And we are going to repeat this process up to the last equation, right? So from the last equation, we'll be able to solve for the xn. So proceeding in this manner, we solve for all the xi's in this vector x. Okay. And this procedure which we are applying here, that you solve for the first equation and then you solve for the second variable from the second equation. So this is basically we are doing the forward substitution, right? So this is known as the forward substitution procedure. So this procedure of obtaining the solution, this is called forward substitution. Okay. And the other case, when we have upper triangular matrix, that we have already seen, that in that case as well, we can solve the system very easily. So if we have invertible upper triangular matrix, so in these matrices basically have this form. So the entries below the main diagonal, they are 0. So let's take the diagonal to be UII. So the first row is going to be U11 up to U1n. Second row will have the component is starting from U22 to U2n. And the last row will have the only non-zero component is going to be UNN. Okay, and here since this is an invertible matrix, so UII, they are not equal to 0. For all I. And if you consider the linear system in this case, that is if you consider AX is equal to B, so we can solve it by back substitution that we have already seen, right? So we solve this by, so let me explain quickly. So the first, what we will do, we'll solve for xn from the last equation. From the last equation, we will get xn as bn divided by unn, right? And now we substitute this. In the second last equation to solve for xn minus 1. So we will get xn minus 1 as bn minus 1 minus, so we will have un minus 1n times xn. So xn is bn divided by unn, the complete thing divided by un minus 1, n minus 1. Okay, and this is how you have to solve for the other variables xn minus 2 up to x1. Okay, so proceeding in this manner. We solve for the solution x. Okay, and we have already came across the name of it, and this we call this as a back substitution, right? Backward substitution. Let me write here. So this procedure we are doing here, this is called the backward substitution. So if the matrix A has any of this structure, whether it is a lower triangular, upper triangular, it is diagonal, we can solve it very easily. But note that in general, the matrix might not have any of these structure, right? We can have any invertible matrix. It doesn't necessarily have to be the lower triangular or the upper triangular, right? So in that case, how can we solve the system? Again, the aim is that we want to solve the system easily, right? So can we do something so that we still want to use this structure of the upper triangular and the lower triangular, and we can get the solution quickly? So this we are going to understand in the LU factorization. So if we are able to factorize the matrix in the lower triangular and the upper triangular matrix, then we can use this backward substitution and forward substitution suitably to obtain the solution. So let's see what we are aiming and how do we achieve that. So suppose we are again interested in solving the matrix equation Ax is equal to B with the coefficient matrix as A. Okay. Now, in certain situation, we can find the lower triangular matrix L and an upper triangular matrix, let's denote it by U, such that I can write the matrix A as the product of this lower triangular matrix L and the upper triangular matrix U. Okay. So suppose I can write the coefficient matrix A as the product of L and U, where L is a lower triangular matrix and U is an upper triangular matrix. Then if I want to solve Ax is equal to B, so this becomes that you have to solve LUX is equal to B, right? So in this case, the system Ax is equal to B, this will become this. Okay. Now, if I call Ux as the new variable, let's call it Z, because U is an upper triangular matrix, X is a vector. So I can form a new system by calling this as Z. Okay. So then this here, what I will get that Lz equals B. Okay. So note that solving this is equivalent to solving these two systems. So this is equivalent to solving the following two systems. Okay, so we have got that Lz is B and Z here is satisfying this. So note that B is given to you. So you can first solve for the Z using this lower triangular system with the lower triangular matrix. And once you have found Z, you solve for the X using this system with the upper triangular matrix. right? So we are going to first solve the lower triangular system Lz equals b for the vector z. And this you can obtain by the forward substitution, right? We have already seen that when you have a lower triangular system, you can easily solve it by the forward substitution. So you can use forward substitution to solve it. Now, once we have obtained z, we can solve this system ux is equal to z using backward substitution for the vector x. Okay. So after obtaining z, we solve the upper triangular system ux is equal to z for the vector x. And this you can do it by using backward substitution. Okay. And if the matrix A can be factorized in this way, that is, if you can write the matrix A as the product of the lower triangular matrix and the upper triangular matrix, you call this as the LU factorization of the matrix. Okay, so this is the definition. So a matrix A is said to have LU factorization or it is also referred as LU decomposition if there exists a lower triangular matrix L and an upper triangular matrix U such that A can be written as the product of L and U. Okay. So here is one remark. So suppose we have a matrix A which has the LU decomposition. That is, I can write A as L into U. So this matrix decomposition, LU decomposition of the matrix is not unique, right? So if you have A as L into U, where L is a lower triangular matrix and the U is upper triangular matrix, so L and U is not unique here. So the matrices L and U, they are not unique. Why they are not unique? Can you just give me any quick argument? Can we find any other lower triangular matrix L Suppose we have L and U, right? My claim is that this is not unique. We can write find another lower triangular matrix and another upper triangular matrix, so that again I will be able to write A as the the product of those two matrices.
Yeah, ma'am.
So how?
Actually, LU decomposition में हम U में diagonals रखते हैं और L में 1 1 1 entries रखते हैं. Then we change this. L में diagonals element रख लेंगे और U में 1 1 1 रख लेंगे तो change हो जाएगा.
Okay, so first of all, when I write, when I say here L into U and L is a lower triangular, U is an upper triangular, diagonals, they don't have to be necessarily one. Okay, in the matrix L, you can have the diagonals as the general element, say L1, L11, LII, okay? And in the U, you can have the general elements as UII. So what you are telling is that that is a way of making it unique. So as we are telling that this is not unique, right? So let me first justify that why they are not unique. So if you have A as LU, and if I take any invertible diagonal matrix, okay, and let me do the multiplication here. So I'm multiplying, post multiplying the L by the D, and then I'm multiplying D inverse with the U. Because if D is an invertible diagonal matrix, then D inverse is also going to be a diagonal matrix. Okay, so this is still remain the lower triangular matrix, and this is still remain the upper triangular matrix. So if I call this as L tilde and this as U tilde, this is the same as L tilde into U tilde. And D is any invertible diagonal matrix. Okay, and you can note that this L tilde and U tilde, they are the lower and upper triangular matrices. This is also an LU decomposition of the matrix A, as L tilde is a lower triangular matrix. And U tilde is an upper triangular matrix. Okay. So now to fix that, which representation I want to have it. So there's a particular LU decomposition. So we call it as a Doolittle's factorization or Doolittle's decomposition. So this is a special case of the LU decomposition. So this is on the name of the author Doolittle's. So this is called the Doolittle's factorization or Doolittle's decomposition. So as I said, this is again a LU factorization, but as as one of you were mentioning that I'm going to fix the diagonal of the lower triangular matrix to be unity. That is, all the diagonal elements of the lower triangular matrix, we are going to take it to be 1. Okay. So let's first write down what is a Doolittle's factorization. A matrix A is said to have a Doolittle's factorization if there exists a lower triangular matrix L with all diagonal elements as 1 and an upper triangular matrix U such that A can be written as L into U. Okay, so see, you can also seek the representation of the A as L into U, where U is having the diagonal entries to be 1. Okay, so there's that is called a different representation, which is called the Crowd's representation or Crowd's decomposition. Okay, so in case if you are interested, you can check that out. So here you take the diagonal elements of U are 1. But we are just going to discuss the Doolittle's factorization because the idea for the Crowd's decomposition is the same. So now the question arises that when can you have, what is a sufficient condition for the LU factorization, right? So when can we ensure that a matrix A will have a LU decomposition? So let me state this as a theorem. So if the matrix A is going to have the leading principal n minus 1 leading principal minus to be non-zero, then we can make sure that the matrix will have the LU decomposition. So that is the only requirement we need to have on the matrix A. So let n greater than equal to 2 and A be a n by n matrix, which is such that all of its first n minus 1 leading principal minors are non-zero. Okay, then A will have an LU decomposition where L is a lower triangular matrix with the diagonal element as 1. L is a, let me call it as unit lower triangular matrix.
Okay.
So unit, when I say unit lower triangular, this means I'm referring that the diagonal entries are 1 and U is an upper triangular matrix. So basically, what I'm referring here is the Doolittle's factorization. So that is A has Doolittle's factorization. Okay. So now let's try to understand that suppose we are given the matrix A, how do we find the Doolittle's factorization of that matrix A? That is, we are going to compute LU factorization. In particular, we are discussing the Doolittle's factorization. So we are going to consider a 3 by 3 matrix, because if you can understand for that, the same idea can be applied for the higher order matrices. So we want to write matrix A as L into U. So it's simply, we have to algebraically multiply it and see how we can compute the entries. So the A is given to you. So A11, A12, A13 is the first row. Second row is A21, A22, A23, A31, A32, and A33 is the last row. And I want to write this as a diagonal matrix, sorry, the lower triangular matrix L having the entries, diagonal entries to be 1 and then upper triangular matrix. So this lower triangular matrix is going to be 1, 0, 0, L21, 1, 0, L31, L32, 1. And the upper triangular matrix is U11, U12, U13, 0, U22, U23, 0, 0, U33. So knowing the AIJs, we want to find the LIJs and the UIJs. So this simply you have to do the matrix multiplication and you have to observe. So if you multiply the first row of L, that is I'm multiplying first row to all three columns of the U. To first, second, and third column of U. So what I will get? So since the first row is 1, 0, 0, so I'm simply going to get U11, U12, and U13, right? So I get U11 as A11 and U12 as A12 and U13 as A13. Okay. Now if you multiply, so the first row of the U is determined now. So if you multiply the second row and the third row of the L to the first column, okay. Second row and third row of L to first column of U, because U11 is already determined. Okay, so this will give us that L21 into U11, this equals A21, and L31 into U11, this is equal to A31. So you can determine the L21 and L31 from here. Okay, and likewise, if you multiply the second row of L with second and third column of U, so note that I'm multiplying the second row with the second and third column. So I already know L21, right? So I will be able to determine U22 and U23 from there. So I will get this as L21 times U12 plus U22, this equals A22, and L21 times U13 plus U23, this equals A23. So L21 is known to you, U12 and U13 are known to you. So you can compute U22 and U23 using these two equations. Okay. And finally, we can determine the L32 and U33 by multiplying. So only the third row of L is remaining. So third row of L, you have to multiply this with the second and third column of U. So you have to multiply. So this is going to give us these equations, L31 times U12 plus L32 times U22 this equals A32, and L31 times U13 and L32 times U23 plus U33, this equals A33. Okay, so from these two equations we can solve for so they give us the values of L32 and U33 because the rest all the entries are already computed. Okay, so basically we have found the first row of the U here, and this gives the first column of the L, and from here we can compute, we are computing the second row of the U, right, and third row of the U, and the last second column is compute of L is computed from here. So basically we have determined all the entries here. Okay, so I'm just giving you one example here where you can apply this Doolittle's factorization. Okay, so one more remark here that if you observe, so here I have to compute, if I want to compute for the L21, I have to divide by the U11, right? And in these equations, if I have to compute the L32, I will be dividing it by the U22 here. Okay, so this means that I have to assume that these two entries are non-zero, right? They have to make sure whether they have to be non-zero entries. So we have them as to be non-zero because I'm considering a matrix A. So basically, if you realize what is U11, let's write it down. So in this process, we must have that U11 is not equal to 0 and U22 is not equal to 0 in order to solve for L. Now, my claim is that this is already U11 and U22, they're already non-zero. If I assume that my A is having first n-1 leading principal minus to be non-zero. Can you justify that? Which is true because we have the assumption that all leading principal minor of A, they are non-zero. So if you just try to see what is U11, U11 is the same as A11, right? So U11 is not equal to 0. Basically, I'm demanding that A11 is not equal to 0. So what is A11? A11 is nothing but the first leading principal minor, right? So if we have this assumption that all the n-1 leading principal minors are non-zero, so you can see that that basically coincides with the same assumption which we have in the even in the Gaussian elimination, right? If you just try to see the coefficients in the Gauss elimination as well, because this Doolittle's factorization is nothing but the, you can see this is nothing but L21, L31, L32. These will be nothing but the multipliers which we have in the Gauss elimination, right? So this is nothing but the same representation what we get after the applying the Gauss elimination. Okay, so it goes back to the same requirements what we have in the Gauss elimination. But note that if we assume that the matrix A has n-1 principal leading minors are to be non-zero, then we don't have to keep any assumption. It's eventually getting hold because A11 is nothing but your So first requirement is A11 is not equal to 0, which is nothing but the first leading principal minor. And then if you try to focus on A22, 2 which you are getting in the Gauss elimination, which is U22 here. Okay, if you just try to simplify, this is going to be the second, you're going to just require that the second leading principal minor is non-zero. Okay, likewise, all the assumptions which we have in the Gauss elimination, that is, if you look at for the general case, UKK, which is going to be the AKK, the K. So this is going to be non-zero with the assumption that the kth leading principal minor of A is non-zero. Okay, so just with this assumption that A has all the leading principal minors to be non-zero, we have that the Gauss elimination and LU factorization, they all make sense. Okay, so here is an exercise for you. So you have to find the Doolittle's factorization of this matrix. So A is 1, 1, minus 1. Second row is 1, 2, minus 2. And the last row is minus 2, 1, 1. Okay, so you have to apply the same steps which I have. You can simply, you have to multiply it properly so that you can obtain all the unknowns in the lower triangular matrix and the upper triangular matrix. And once you have the upper triangular, the factorization of the matrix A as L into U, then you have to solve AX is equal to B with B as 1, 1, 1 transpose using the obtained LU factorization. Okay, and for this you have to follow the same steps what I explained before, that you want to solve LUX is equal to B. So you break this system into two systems. So first you solve, so I'm defining Z as UX. So I'll be solving for LZ equal to B. So once you know L, you can solve for Z from here. And once you have found Z, you solve for X from here. Okay, so just complete this exercise. So if you have any questions, you can ask now. Okay, if not, then we stop here. Thank you.
Thank you, ma'am.